Okay, let's start. Today we will see the principal component analysis or called the PCA algorithm. Okay, so this is another unsupervised learning algorithm. So actually this is also called the dimension reduction or the compression algorithm. So today let's see the what it is. Okay, so the principal component analysis we'll call the PCA is a popular method for the dimensional voltage reduction. Okay, so what is the dimensional voltage reduction? Okay, let's see the detail. First of all, let's say we have a matrix X, which is the T by N data matrix. What is that? The N columns represent the input or the feature vectors in the D-dimensional space. So let's say we have a matrix X, something like that. So each matrix 1 consisting of the column vector x1, x2 through the xn. So the 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 dimension of this column vector is the d dimensional column vector, and the size. What is the size of the this matrix? T by n, right? This is the large n, right? So we have the data matrix here, right? Then if you remember our previous lecture in the k-means clustering, okay, let's say k-means clustering. Here, this is the one examples of our data matrix X, right? Here, right? Okay, let's say we have the matrix X, and given this matrix, we are looking for the linear mapping of the d-dimensional input vector into the k-dimensional space when k is smaller than the d. Okay, so we want to find the mapping function xn through the let's say yn using some linear mapping okay, so let's say this is the rd, this is the r k when k is smaller than the d, right? The finding this linear mapping function is the goal of the PCA algorithm. Okay, so what is the desirable property of the this yk? The first of all, this yk should best represent the original data. In other words, we compress data with as small as possible distortion. Okay, so we want to minimize the distortion or the error from the xn to the yn, right? So this is called the compression. Okay, this is the first goal of the PCA algorithm. Another goal is that to look for the linear transformation that has the maximum variance or the decorrelate the input. So this is another goal of the PCA algorithm. So today we will see what does it mean. Okay. First of all, let's start with the motivation. Okay, let's say in the above figure, let's say there are vector xn, in this case R2 space, right? So this vector consisting of the x1 term, x2 term here, right? Let's say this is the x1 and x2, right? Then what you want to do is to reduce the data from 2D space to the 1D space. So this is a data compression problem. So then how can I find the 1D representation for each sample? We can find the mapping function, mapping straight line, something like this, or something like that, or something like something like that. Okay. Let's think about this one first. Then we can project. We can project to this straight line, something like that, like this. Or when we think about this one, we can project each samples to the here, right? So what we want to do is to find out this straight line that maximize their distribution of the samples in the projected space, right? So this is the goal of the PCA algorithm. So when we use this straight line, the 1D samples is looks like that, right? So the new term is something like that. Okay, so this one is the R2 space and this is the R1 space. Okay, so from R2 space to the R1 space, we need a new projection method or the projection matrix, right? Then this projection matrix that preserve the relationship between the samples, right? So in this case, we want to maximize their variance in the projected matrix, projected space. Okay, so this is the motivation of the PCA algorithm. Another case is that this is the 2D to 1D, and we want to find the 3D to the 2D. Okay, let's say we have the three-dimensional vector xn is R3 space. Then let's say this is the x1, x2, x3 space, right? Then we want to project this three-dimensional feature to the 2D features. But when we rotate this one, something like that, in this case this is x1, x2, x3, we can see there is some kind of the lower dimensional structure in the 3D data. I mean, we don't need this higher dimensional space to preserve the relationship of each samples. And then we can introduce a new projection method that preserve the relationship of each sample while reducing the data memory consumption. Okay, so here we want to find out the new space in 2D, something like that, or something like that. So this is the same plane but in the different view. Then finding the new axis or the new coordinate x1 and x2. Okay, let's say y1 and y2. And by projecting each samples to this plane, we can find out the new coordinate and samples here can represent the samples here. Okay, comparing to the 3D space, this 2D space also contain the information of the each samples, but there might be some the error or the projection error or the distortion. But what we want to do is to minimize this distortion in the projected space. Okay, this is the goal of our PCA algorithm. Okay, so yeah, what is the PCA algorithm? Okay, we already discussed what it is, right? What is that? Let's assume that the projection matrix or the projection line through the zero point. We can think about the several straight lines. First one is something like that, or the second one is something like that. So the question is, which one is better? Which one is the better projection in terms of the variance? When you think about this red line, the projection is here, 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 right? So these 5 points in the 2D space represent in the 1D space, something like this. So when we read through this red line, so the values are something like 30 values, something like this, right? What about the blue line? What about blue line? These terms project here, 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 here. Here, right? So they are projected to here. So when we read the blue line, the data pointer here, right? So which one is better? Which one is better? This one. Why? This red one contain the relationship of the samples in the 2D space, right? Because in 2D space they are similar, right? So in the projective space they are still similar, right? But in the blue case, there is no distinct property or the distinctive features in the projective space, so we cannot use this blue line to understand the original data distribution in the 2D space. Okay, so we want to find this red one rather than the blue one. Okay, this is the goal of the PCA algorithm. People starting the PCA, I want to emphasize the difference between the PCA and linear regression problem. Okay, we already know what is the linear regression problem. Okay, let's say we have a point in the same position here. So in the linear regression problem, we want to find the linear mapping that minimizes the difference between the estimated y and ground truth y. So here something like the difference here between the ground truth y with the estimated y, right? So this is the loss between estimated and ground truth y. So this is the linear regression problem, and in the PCA, we want to find out the mapping that have the high variance in the projected when projected each sample to the red line here. So comparing to the linear regression here, you measure the projection error here. So this is the difference between the PCA and linear regression algorithm. Okay. So actually, this is they have the different goal, right? So yeah. Okay. So before starting, I want to introduce SVD algorithm, single value decomposition algorithm. Actually, the SVD is the key in the PCA algorithm. I guess some of you or the most of you already know the SVD. What is the SVD? So today I'll just briefly introduce the SVD and what is the role of the each component in the SVD. Okay. Okay. First of all, recall that any D by N matrix F can be written in the form X is equal to the U times S times VT. Okay? Let's say we have a matrix T by N where this is Xn in the RT space, right? And this is the large X here. Then the SVD means we can decompose this one to the T by T matrix U and T by N matrix S and N by M matrix V transpose. Okay, so this U matrix consisting of the mu k here, and this S matrix consisting of the diagonal term, so sk here, where other term is zeros here, and V transpose also consisting of this one, right? Column vectors, right? So first of all, these two matrices U and VT is orthonormal. What is orthonormal means? What is orthonormal? Mu ij mu I transpose mu j, a different column vector, mu I mu j is the 0 when I is not equal to j, and 1 when I is equal to j. Okay, so this is a property of the orthonormal matrix, the similar equality defined in the matrix VT. Okay, so the one property is the matrix U and VT is orthonormal matrix, and this S matrix is a diagonal. Okay, so this is a singular value decomposition single value decomposition method, right? So S is the size T by D, V is the size n by n, right? The S is the size T by n with a non-negative entry along the diagonal here, right? So this is the singular value decomposition. Any D by n matrix can be decomposed to the three kinds of the matrix U, S, V, T, right? So these diagonal entries are called the singular value here. This is called the singular value, right? And columns of the U and V are called the left and right singular vectors. So this is called the left singular vector, and this is called the right singular vector, right? Oh, because this is VT, the column vector of the V matrix V is something like that, right? So this is the left singular vector here and a right singular vector in here, right? So by convention, the single value appears in the descending order in S. That is, we have the S1 larger than S2, larger than S3, something like that. So when you think about the S matrix, S1 here, S2 here, SD here, and zeros in here, because the size of the S was the T by N, right? Right. We assume that N is larger than T. Okay, right. In here, this term is larger than here. Okay, so this is a single value decomposition. And what's the meaning of the single value decomposition? Okay, let's say we have the original data distribution here, and we want to apply the linear transformation, just call the matrix M here, then new distribution with something like that, right? Then the singular vector decomposition do was what the SVD do is that we can decompose this linear transformation to the three terms V transpose, sigma transpose, and mu U transpose. Okay, let's say we have a input matrix A, right? Then this is MA, right? Then rather than just compute the MA, we can compute the mu U sigma V transpose A. So first of all, VT A are here, and sigma VTA are here, and mu VTA is here, right? So in the V transpose and U transpose, they just rotate this shape without any scaling, right? In here they just rotate here, and in the sigma, by using the sigma or the S in here in this definition, we can extend or the shrink of each direction by in terms of the main diagonal direction. So the reason that we use the SVD is to decompose each transformation component step by step. Okay, so in the PCA we will use this one. We will use this U matrix. Okay. Then let's find out the SVD PCA algorithm. So the goal is to reduce the data matrix X when the size of the X is the D by N. Then we want to reduce this X from the d-dimensional space to the k-dimensional space, right? Right? Something like the 3D to 2D or the 2D to 1D, right? So what I want to do is just to pre-process the original matrix or the original vector xn. This is just one column xn, right? So first of all, we can compute the mean values of this xn, right? Then we can replace the original xn with the xn minus mean of xn, or the just the average xn, right? Then let's decompose this original this vector x as a USVT by using the SVD method, right? By using the SVD method, and in the mu matrix, which is consisting of the T column, right? T by T, so it consisting of the mu k when k is equal to 1 through the t, right? Then what PC want to do is to just extract the first few vectors from the original U matrix. Let's say let's extract the mu1, mu2 through the mu k, mu large k here. Then this matrix will be T by K matrix. Okay, so let's say this is a large UK. Okay, and then what I want to do is just matrix multiplication with the original matrix X and UK transpose here. So what is the size of the UK transpose? K by T. And what is the size of the X? T by N, right? So, and then the size of the Y matrix Y is the K by N, okay? So, in other words, the Kn the Y is something like this. Yn, the size of the X was the T n, and size of Y is the K n. So this Y is the new input features that is projected to the k-dimensional space from the d-dimensional space. Okay, so this is the PCA algorithm do. So the main the key ingredient as here. Why we need the mu k? Why we just use these first few UK from U1 through the U large K? Why? Actually, this is due to the property of the SVD. In here, in SVD, the main component, the very important information are first few vectors. What does it mean? Okay, let's say this is the first UK, and this is the first SK, and this is the VK. Then by using this one T N, we can reconstruct the T by N, right? From the next one, we can also reconstruct T by N like this. T by N, because this is a matrix multiplication, then we have to find the summation from this one. So because of the SVD property, this one and this one, first few reconstructed value can approximate the original matrix X. So it means that by using the first few mu k, sk, and the vk, we can find out the good approximation of the original matrix X. Okay, so it means that by using this one, we can project the original matrix X to the new Y. Okay, so this is the key ingredient of the PCA algorithm. Okay, from now on, from several pages, so we will see the why PCA algorithm is the important, and PCA algorithm have the dimensionality reduction property comparing to the no, not comparing. We will see the why the PCA algorithm have the advantages when we do the dimensionality reduction. Okay, let's see. First of all, let's find the relationship between SVD and dimensionality reduction. Actually, the dimensionality reduction is to look for the linear transformation given K by D matrix. Called the comparison matrix. Okay. Let's say we have an original matrix X, and with the K by C matrix, we can compress this X to the new space, right? Then the second linear transformation given the T by K matrix R reconstruction matrix here, right? So this is the compression, and this process is decompression, right? So our goal is to find out the matrix C and matrix R that minimize this loss function, right? So this is the goal of the dimensionality reduction, right? So what is this one? This one? This one? This is just defined up like that. Summation of the every component in the matrix A. So this is very simple. But anyway, so this is our loss function. In other words, we want to compress the D by M matrix X into the K by M matrix CX here, K by matrix CX, such that the data is represent as peaceful as possible. So this is just the PCA algorithm, right? T by N matrix to the K by M matrix, something like this. Okay, so let's think about what it is. So there are lemma. Actually, this lemma is really important, but it might be hard to prove here. So the proof is beyond our course. So, but we can just use this lemma to prove our dimensionality reduction and SVD relationship. The lemma is something like that. So for any D by M matrix X and any D by M matrix X have the difference, the distortion, original matrix X with the approximated matrix X hat is larger than X minus UK transpose X, and which is equal to the summation of the SI. Okay, where X can be represented as VD here, right? SI is the singular values, right? And μk is the K D by K matrix consisting of the first K columns of U. Something like this, right? So this is the lemma. So we will use this one to see the relationship between SVD and dimensionality reduction. So by the way, the AUK is the part few terms here in the matrix U and matrix UK here. Okay? So this lemma tells us that the most important information about data contained in the projection onto the first singular vector, the second most important information contained in the projected onto the second left vector. So what does it mean? Record that the first column here, small k, the first column is just U1, right? U1 contains the most important information about the data, and the second most important information is contained in the UK, right? So by using this first few UK, then we can extract the principal or most important component from the data. Okay, so that's why this algorithm just called the principal component analysis or the PCA algorithm. Okay, so why this one? This first few UK is contain the important information than the remaining one here. So we will use this lemma. First of all, let's say matrix SK be the KN diagonal DN diagonal matrix, which is equal to S for the first K diagonal entries, but is the zero thereafter. So this is original matrix, original matrix S. There are S1, S2 through the ST, right? So when we just S1, S2 through the SK with zeros here, which will be the new SK, right? So if we rewrite this one, S1, S2 through the SK and 0, 0, 0, 0 with other part is also 0, right? Okay, let's introduce a new SK here. Then what is the UK times UK transpose X here? Then we can decompose X something like US with T, right? Then what is that? Understand? This is just I k times k and 0. If you remember, the matrix U is also normal. Where's that? Also normal here. Then you can easily derive this one. Anyway, then what is that? Then we can represent this one to this one, U S K V transport. So this is called the truncated SVD. So it means that we decompose X to the D by D, T by N, N by N. By using the every information, we can perfectly reconstruct the original matrix X, right? But in here, we want to just use the few values here to reconstruct the new X here. Let's say in here xk, right? So the lemma state that the best approximation to the matrix X, this one, the best approximation, this is approximation. The best approximation is obtained by computing the SVD and by setting all singular value Sj when j is larger than k plus 1. So by making this one as 0, it means that we will ignore this term, right? Because this is all 0, so which will be also eliminated when computing the matrix multiplication, right? So what does it mean? So from here, this difference or this distortion is equal to the summation of the sigma I here k plus 1 through the t, right? So by eliminating this term, by minimizing this term, we will also minimize the by making this term as a 0 here, this one will be the 0. So this is the lower bound of the distortion between the X and the reconstructed value. Okay, so that's why the PCA algorithm have the small distortion error, right? Then another good benefit of the PCA algorithm is the decorrelation. So when you assume that the d-dimensional vector X generated in an IID fashion, so what is the IID? Do you know? So IID means, what is that? Independent, identical distribution, right? So this is the independent assumption, right? Anyway, so according to the sum unknown, the distribution Xn, then so first of all we have the T by M matrix X, right? So let's compute the empirical or sample mean or covariance. So the mean is something like that and covariance something like that, right? Then because we pre-process the original matrix X by subtracting the mean from each row, right? Then using SVD, the empirical covariance matrix here can be written as follows. So nk is equal to blah 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 here, because there is no mean here, because we already pre-processed the data with the by subtracting the mean, right? So it can be represent x times x transpose here. So what is x? X is a USVT and xt is the v STUT, right? Then because this is the identity matrix, right? M by M identity matrix, then this term is something like that and something like that, okay? Where this one is the D by D diagonal matrix consisting of the D first columns of the S. So here, right? But with the square term, right? So it means that so SD square means the S1 square, S2 square, something like ST square, 0, 0, 0, right? Anyway, so now consider instead the transformed data, the projected data using the linear transformation U transpose, right? Using the PC, right? Then we had a sample covariance matrix, something like that, new covariance matrix, right? So something like that, something like this, right here. So comparing to this one, new covariance matrix, something like that. We don't have this U in here, right? So which means we have linear transformed data in such a way that the empirical covariance matrix is diagonal, right? That is, the various components are uncorrelated, right? So what does it mean? So this is a covariance matrix, right? But the covariance matrix is something like the diagonal from here, and there are 0 here. So it means that, okay, this is the i's component and this is the j's component. When there is some value, this correlation of I sample and j sample, i's component, right? But in the sample covariance, there is no values in here except for the diagonal term, right? So it means that each component, i's component, j's component, are uncorrelated. So what does it mean? Let's say xn is the x1 through the xt, right? And x hat, a new x hat is the x1 through the xk, right? It means that each component uncorrelated, uncorrelated. Okay, so and the empirical variance of the first component equal to this one, right? Because this is defined here, right? So this means that the whole of component or whole the component in X hat, the first component has the largest variance. So it means that the first component, first vector, first UK contain the largest variance, so that maximize the data distribution of the previous original the RD space. Okay, so this is why the PCA can decorrelate the original input data in the projective space. Okay, so this is the I can actually the PC algorithm is very easy and very easy to implement, but it has a very powerful property, something like this. Actually, from here we see why the PCA algorithm have the few several benefits. Actually, this proof is really hard to the really hard to follow and understand. I understand what is that. So I suggest you just understand what does it mean and remember the PCA algorithm is looks like that, but the in behind there are several the mathematic property that make the PCA is good to dimensional reduction. Okay, so actually the PCA algorithm are very popular and have been used to the several application. The one of the most popular application is eigenpace. Actually, this is the face recognition or the face verification paper in the CBPL 91. So actually 30 years old, right? So, but this paper is also, even though the paper is old, very old paper, they are based on very powerful mathematical background based on the PCA algorithm. So here we have the 50 by 50 input vector because this is image, but this is just vector, column vector, xn. When t is equal to 50 by 50, so 2500, right? So what is the shape of the x? Something like t by n matrix. So when t is the 2500 and n is the number of samples. So we have this one image here, right? Then we can compute the SVD, right? How? U S V T, right? So when you think of the U, it will be like that. So T times D, we can use the several things here. Then let's say this one is the D by K, right? So it will be the new mu K, right? So by using this one, we can project the original image to the new K dimensional space. Let's say K is equal to the, in this case, K is equal to 10. So comparing to the original 2500, the 10 is the very small area. So it means that we can compress the original image to the smaller dimensional space like that. Then, so what is the desirable property of this K 10 dimensional space? It should be reconstructed well to the original data. So here is the example. This is the original xn. This is the UK transpose and xn. So this is the projected vector, and this is the reconstruction vector. So this is the reconstructed images. So comparing to the original image, the reconstruct images well approximate the original images. So I can so PCA algorithm is powerful to compress and reconstruction. Okay. So by the way, so in this paper, this one is called the eigenpace. So eigenpace. So this is very popular method. But it just used the PCA algorithm. So if you are interested in this paper, please or read this paper and try to understand what does it mean. Okay. So this is a very powerful application in eigenpace. Okay, so this is the end of the principal component analysis. So actually, this is the end of the first part in the discourse. So in the first part, we discussed what is the handcrafted model in the supervised learning and unsupervised learning. So from next week, we will start the deep learning stuff, something like the what is the neural network, what is the basics, what is the representation, backpropagation, and activate function. So, but as I discussed previously, this deep learning stuff are built from our previous method. So it means that people starting the deep neural network, you must fully understand what is the linear classification, what is the logistic regression, what is the SVD, Cambridge clustering, or PCA, something like that. So I strongly suggest you people taking our next few lecture, please go back to our previous lectures and try to fully understand what does it mean, and then let's start our next lecture. Okay. Before finishing today's lecture, I will briefly summarize our first part of course in Korean. So 이제 저희가 오늘은 이제 1시간 정도로 시간을 들여서 이제 PCA에 대해서 정리했습니다. 그래서 결과론적으로 보면 PCA의 알고리즘은 정말 간단해요. 정말 간단해서 사실 SVD라는 것도 저희가 짤 필요가 없이 SVD는 저희가 가지고 있는 대부분의 코딩 툴에서 다 제공을 하고 있고요. 그래서 우리가 간단한 프리프로세싱과 SVD만을 통하면 사실 PCA를 위한 리니어 매핑 펑션을 저희가 찾을 수가 있고, 즉 리니어 트랜스포메이션 매트릭스를 찾을 수가 있고, 이제 이걸 이용해서 저희가 간단하게 어떤 라지 스케일의 데이터를 좀 더 스몰한 디멘셔널 스페이스로 프로젝션 시킬 수가 있는 거죠. 근데 이러한 알고리즘이 가지고 있는 SVD를 사용하는 특성이 사실 오늘 우리가 좀 어렵게 봤던 이러한 특성들 때문에 데이터를 왜 에러를 미니마이즈하는 관점에서 왜 데이터를 잘 컴프레션을 하는가, 그리고 컴프레션된 데이터가 왜 서로를 코릴레이션을 없게 만들어 주는가라는 게 사실 이제 많은 수학적 백그라운드에서 시작했다고 제가 볼 수가 있습니다. 그래서 사실 저희가 뒷부분에 봤던 이런 증명들은 사실 완벽하게 외울 필요는 없어요. 하지만 근데 이게 왜 이렇게 되는지를 이해를 하고 PCA 알고리즘 어떻게 돌아가는지를 알면 사실 충분합니다. 근데 이제 제가 이러한 계속 알고리즘들을 설명해주면서 이러한 부분들을 좀 어렵지만 왜 자꾸 보여주냐면은 얘네들이 어떤 식으로 자기들의 PCA 방법을 증명을 했고 왜 PCA가 이렇게 잘 동작하는지가 어떻게 버리피케이션이 될 수 있는지를 정확하게 이해를 해보자 이거죠. 항상 제가 얘기하지만 이러한 기법, 그러니까 잘 정립된 방법들을 이러한 따라가는 프로세스들이 사실 조금만 변형을 하면 저희가 새롭게 제안하는 방법들을 버리피케이션 하는데 충분히 사용될 수가 있는 것이죠. 예를 들어서 PCA가 왜 디콜레이션을 가지고 있고 왜 디멘셔널 디덕션을 가지고 있는지에 대한 프로퍼티를 우리가 딥러닝에서 제안하는 어슈바이드 러닝 방법에서의 증명에도 사용될 수 있다는 거죠. 그래서 제가 계속 말씀드리지만 이러한 기존의 방법들에 사용했던 잘 정립된 방법에 사용됐던 어떤 버리피케이션들을 잘 따라가고 이해하는 게 매우 중요하다라는 겁니다. 여기까지 잘 오셨고, 이제 다음 시간부터 저희는 이제 뉴럴넷, 즉 딥러닝으로 이제 들어가게 될 건데요. 이제 딥러닝에서 매우 중요한 방법들을 저희가 하나하나 요소를 보고 마지막 이제 본 코스의 마지막에서는 이제 컴퓨터 비전 관점에서의 딥러닝의 셀렉티브 토픽들에 대해서 살펴보기도 합니다. Okay, let's finish the today's lecture. Thank you.